Hi everyone, we're going to be discussing Lab 3 today. In part 1, we are given a system where a star of the given mass is orbiting a black hole with an unknown mass. The starter code that is used gives us positions and velocities based on our GTE modes. To solve for the mass of the black hole, we'll be using positions and velocities as well as the formulas above to find the net force of gravity and to solve for the mass. Using the velocities, we use the momentum formula where momentum equals velocity times mass. We then find the change in velocity and the change in momentum. To find net force, I use Newton's second law, or net force equals mass times acceleration, and use the change in velocity over change in time because it is equal to acceleration. Next, I solved for the parallel force, which is equal to the difference in the magnitudes of the potentials over the change in time, which is then multiplied by the unit vector of the magnitudes. We know that net force is equal to the sum of the parallel and perpendicular forces, so I use that equation to solve for the perpendicular force. In this part of the code, we are solving for the mass of the black hole. To make things easier, I established the variables for the magnitude of the star's distance to the black hole and the magnitude of the force. I then use the force of gravity formula to solve for the mass of the black hole. When we run the code, we are able to see the change in the vectors for momentum, parallel force, and perpendicular force. Using the code that we made to find the mass of the black hole, we found that its mass is approximately 1.3 times 10 to the 34th kilograms. In part 2, we are in a spaceship that is approaching the same system from part 1. However, there is a planet that is also orbiting the star, and there is a moon that orbits the planet. If we want to put our spaceship into a figure 8 orbit, we need to find the initial velocity of the spaceship if we are taking off from the moon. Here are our values that are given in the starter code. First, we will be finding the force on the moon, which includes both the force of gravity on the moon by the planet and the force of gravity on the moon by the spaceship. First, we find the distance between the moon and the planet and the unit vector and magnitude of the distance vector. We then use the force of gravity formula to find the force of the planet on the moon. The same process is used to find the force of the ship on the moon. The net force on the moon is the sum of the two forces that we just found. Next, we find the new velocities and position for the moon and the ship given a change in time using Newton's second law. You can see the modifications and substitutions made based on the variables that we knew. On lines 55 and 56, we can alter the initial velocity of the spaceship as it leaves the moon. This allows us to see the effect on the orbit based on these values. On the previous slide, we are able to experiment with the initial velocity vector so that we have a figure 8 orbit. After numerous trials, this is the vector that produced the best representation for the figure 8 orbit. Although this is the only successful vector that I could find, there are still other possible velocity vectors. It is also important to note that this is considered a simple model, and it is important to think about how the system would change given that the masses were different or if there were multiple moons or planets. Even though we may never find ourselves in a spaceship, this lab shows how the principles and formulas of physics can be applied to explain the way that the universe works.